In this lesson, we're going to be covering transmission media and transmission technologies. Network media is this transmission media that I mentioned in the title slide there. The media is the mechanism that carries the signal and data across networks from the source node, the sender, to the destination node, the recipient. So very often these are cables of some sort, and in our wireless networks, we actually use the air as the transmission media. But let's dive into this and let's talk about these different types of transmission media right up front here. One aspect of the media that we're going to be exploring deals with the efficiency of the transmission. In other words, how far will the signal go before it degrades so much we can't understand it anymore? And the second aspect deals with the security aspects of the actual signal conveying across the media. So as you look at these different media types, it's a good thing to have in your mind what is the more secure and more efficient transmission media and what is the lesser secure and lesser efficient transmission media. Recognize that more secure and more efficient is almost always going to be more expensive. And the weaker media, the types that are very prone to data theft and data corruption due to interference and static and things along these lines, this is generally your cheaper type of media. So there's always going to be this trade-off. So let's dive into these 5 different types of transmission media, and we'll understand a little bit more about them and how they operate. The first one on the list here is considered to be the most secure because it has essentially no emanations. In other words, it's very, very difficult for a bad guy to steal your data signal as it conveys through the fiber optic cable. And it also is a very efficient transmission mechanism. In other words, it can go miles and miles before the signal degrades to a point where the receiver can't understand it. So what fiber optic cables actually use is light pulses. In other words, it's actually photons that are carrying the signal and the data. So if you want to think of it in very basic terms, think of when the light is on, that's a binary 1. And when the light is off, that's a binary 0. And photons do not produce emanations. Now, what we're going to see in some of these later transmission media types is they use electrons to carry the data signal. Well, electrons have this phenomenon called emanation. And we'll dissect that in just a minute, but photons don't emanate. And as a result, they're considered to be the most secure. They are one of the most efficient media types, and therefore they're one of the most expensive media types. We get very high data rates on fiber optic cables, gigabits of data, and therefore it's a very good vehicle to carry your signal to use as you connect your locations together across the city perhaps, or even within an office. Now typically it's more expensive than we want to spend within an office. The next one down on the list is coaxial cable. Now coaxial cable has been around for a long, long time. It's actually commonly used in your homes to carry your TV signal into the home from the cable provider. It is a center conductor that actually carries the data signal, but then wrapped all the way around that center conductor is a grounded sleeve or shield that helps to keep the signal contained within the coaxial cable. Now, as it holds that energy within, less energy leaks out. Therefore, the emanations, the security component of emanations, is fairly strong. Difficult for a bad guy, not impossible though, but difficult for a bad guy to steal that signal without getting very close to the cable, perhaps even placing into the cable itself. Coaxial cable uses electrons and radio frequency waves on that center conductor to convey the data within the signal. And again, it's these electrons and radio frequency waves push electrons around. And as these electrons flow through the cable, they actually emanate an electromagnetic field around the cable itself, outside in the air around the cable. Now that grounded shield around the coaxial cable tends to keep that collapsed and contained within the shield. However, some will still leak out. So it has very good emanation protection. And however, it still is not emanations free like fiber optic cable. Now, there's another aspect of the emanations, and that is if I can emanate a signal outbound, that says other signals in the area that are emanating might actually induce signal, which is corruption and interference on my signal within the coaxial cable. So these emanations from other sources can actually penetrate into the coaxial cable and start to degrade my signal due to this interference. So coaxial cable is considered one of your better connection media for networks. The next one down on the list is shielded twisted pair, and its very close cousin, unshielded twisted pair. Now this is your standard Ethernet. Your standard Ethernet almost always uses UTP, or unshielded twisted pair. Now, these two are constructed approximately the same, other than the shielded twisted pair has a sort of an aluminum foil wrapping, a conductive wrapping around the wires inside the Ethernet cable. And it's called twisted pair because there are actually 8 wires inside these cables, and we take one wire that's going to carry the data signal and a second wire that is going to be grounded, and we wrap the ground wire around the data wire. In other words, we twist them together as a pair. Now, the grounded wire tends to disrupt this propagation of the emanated field around the data carrying wire. So as we're pushing a signal through that wire, we are using electrons to carry that signal, and those electrons, once again, propagate into the air. Well, again, the grounded wire that's wrapped around it will disrupt that magnetic field around the data carrying wire, and we have some marginal shielding, if you will, because of this grounded wire. Now, the shielded twisted pair is a little bit better as far as emanation security are concerned, but it is more expensive and it's fairly difficult to work with. If you're building these cables, it's a real pain to build these cables. The unshielded twisted pair, hands down, has dominated the marketplace when it comes to connecting your networks together. So the UTP is by far the dominant technology, network media, that's used for corporate networks. Now, a very popular, relatively new entry into computer networks as a media is wireless networks. It uses radio frequency electromagnetic waves propagated into the air, where the air is actually the media itself. And this means it is the least secure because it is nothing but emanations in the air, which means a bad guy with a receiver can listen to everything you're propagating across your network. That's why we have to take extremely high measures to secure our wireless networks. Because we don't have to buy cables and have cables run throughout the building, this is also the least expensive network media that we could implement as well. So it's very easy to assemble a wireless network. It's very easy to tear it down and move it, relocate it, etc. So the wireless networks are the least secure with nothing but emanations, but it is by far the cheapest approach when it comes to media because there's essentially no cost. We're using the air as the media. And again, as we said, these emanations allow for theft of data signal and also allow for inbound propagation of unwanted signal that tend to degrade the signal due to crosstalk and interference. Now, this term attenuation deals with a signal degradation over distance. We're going to look at that in just a few minutes. This lesson is going to cover several of the key terms that need to be understood about network media. So we're going to be looking at these definitions. Now, the first definition we need to address is a common problem with all network media types, and that's called attenuation. Attenuation is a naturally occurring phenomenon, and basically it is degradation of signal over distance. So as you have a longer cable and you are transmitting from one end of that cable at the source to a destination at the other end of that cable, the signal will degrade over distance. So the longer the cable is, the more degradation or attenuation there is with this signal. Now, we can make a cable so long that the signal is so degraded by the time it gets to the destination that the destination can't understand what the signal is saying. So we have to move back then to a shorter and shorter cable until we can be certain that the destination will always understand the signal, that it hasn't been degraded so badly that the destination can still understand what the signal is conveying, the data part of the signal. Now, this attenuation is due to several different types of phenomenon. The first one is called interference. This would be some sort of induced signal due to emanations from some other source. It might be a radio tower. It might be a wireless network. It might be a microwave oven that somebody's using in the break room. But electromagnetic interference in the air, it's all around us, is a source of interference. And if that signal that isn't wanted somehow finds itself on our wire that's carrying our data signal, that by definition is the interference. There's a phenomenon called impedance that is a component of high-frequency data signaling. And if there is high-speed data, of course, on our corporate networks, that's what we want, high-speed data, we wind up with some sort of impedance characteristics or phenomenon occurring. Well, the impedance of the system must be very well tuned so that all components have the same impedance. And if there is some sort of mismatch, we wind up with an inefficient transmission through that area. Maybe it's a connector, or maybe the cable got cut and we had to solder it back together, some sort of splice. These are sources of impedance mismatch. And then, of course, as I said, if we have to put connectors together, the electrons running through our cable must jump from a pin on one connector into the wire on the adjacent connector, where these connectors squeeze these pin in the socket together. Well, this minuscule air gap, perhaps even microscopic air gap, is a source of signal loss. And they call this insertion loss. As the pin gets inserted into the jack, then we have this degradation or attenuation of signal. Now, the next definition down is interference. And as I said, interference is generally unwanted signal on your data carrying conductor. And it very often is induced by some sort of emanation from some other source. As we said, it could be a radio transmission tower. It could be you're very close to the airport and the radio communications between the tower and the airplanes around. It could be radar. It could be a wireless network. Many, many sources of emanated electromagnetic energy in the air all around us. If that signal gets induced into our wires, boom, this is interference. Now, we have this superset. It's called electromagnetic interference. That says, of course, that it uses electron flow and magnetism to push those electrons around. And this is the superset category. This is all forms of this interference. However, there's a subset called radio frequency interference, and a key term here is frequency. If there is any regularity to the interference, it's generally considered to be RFI, radio frequency interference. Frequency being frequently presents itself, and it's sort of some consistent pattern of interference. This is RFI, a subset of EMI, electromagnetic interference. And then we have another subset that is more of a transient noise, a very irregular, staticky, no pattern, no regularity to the electromagnetic interference. So things like a lightning strike, or perhaps we turn on a fan that uses an electric motor and that fan induces some sort of static into our electrical system. This would be a type of transient noise. Again, a subset of electromagnetic interference. This is all bad for your data signal because I want to be able to read my binary ones and zeros out of my signal that's carrying my data. Well, if these signals are inducing themselves into my wires, this is doing nothing but causing confusion and havoc in my attempt to understand my emulated signal and the data that that signal is carrying. We've already discussed emanations to a large extent, but basically this deals with the electron flow through a wire induces or emanates a magnetic field in the air around the conductor carrying the electron. Now that in itself is an emanation. And if it was all by itself left alone in nothing but air or a vacuum, it wouldn't cause us too much of a problem. However, because we have many wires that might be adjacent to one another, like a cable run, a bundle of Ethernet cables running through the walls or through the ceiling, and they're generally packed tightly together, the emanated signal from one wire induces signal interference into adjacent wires because they cross this airspace where this magnetic field is built. So these emanations cause interference and signal degradation. As the second wire gets interference induced into it, essentially that second wire stole energy from the first wire that was emanating. So the signal is being degraded in the first wire due to energy lost in the second wire. And the signal in the second wire is being degraded because it now has electron flow that isn't part of the intended signal. So emanations are a problem in this regard. Further, emanations are the source of data theft. So a bad guy, without actually even touching the wire, can use a detector and sense these electromagnetic fields around the wires and can identify the presence or absence of electron flow, which essentially is your signal carrying the data. So the bad guy can actually steal your data just by sensing these emanated signals into the air. Again, this is a security concern in addition to be a degradation of signal. And as we described these emanations, I also described what is called crosstalk. As I'm sending an intended signal down a wire carrying data, it induces or emanates a magnetic field in the air around that wire. Well, an adjacent wire that penetrates that magnetic field is going to have energy induced into its data carrying signal, and this is called crosstalk. When one wire induces signal, unwanted signal, in the second wire, this is called crosstalk, and this is that degradation of signal and the theft of energy, and again, could be used to steal the actual data. So these are some of our core terms for network media, and these have implications relative to efficiency of transmission as well as the security aspects of the particular media. This lesson covers several more terms related to network media. In this lesson, we're going to be looking at the difference between baseband and broadband media types. Let's first look at baseband. Baseband transmission technologies allow only one signal on a conductor at a time, on the media at a time. And if a second signal is transmitted onto the media while a first signal is present, both signals are destroyed. In other words, the recipients can no longer understand what the data is that the signal is supposed to be carrying. So both signals are destroyed. This is referred to commonly as a collision on a network. So on baseband networks, only one node is allowed to transmit at a time. And if two nodes transmit at the same time, both transmissions are destroyed. Both transmitting stations need to stop transmitting and allow the media to stabilize, and then they can, over time, try to begin to access the media again, hopefully not colliding with somebody else's signal. So we're going to be looking at ways that this may occur later on. Now, one technique to allow multiple nodes to share the same common media for baseband is using something called time division multiplexing. What time division multiplexing does is it takes, let's say, a 1 second period, and it breaks it up into, let's say, 10 different time slices. And it then will allow node number 1 to transmit during 1/10 of that 1 second period. One time slice is what it's called. And then it says, all right, you have to stop. Then it goes to the second node and says, all right, it's your turn to transmit. And now the second node transmit, but the other 9 nodes are not allowed to transmit during that one time period. By using some mechanism of identifying whose turn it is, time division multiplexing allows multiple nodes to share a common baseband media. And the media access methods are commonly used and have been used historically, will be explored in later videos. So some technologies that use baseband are Ethernet. Now, Ethernet, as we said, is probably the single most commonly used network media for all of our networks. We might have long data runs where we use fiber optics or wireless or SONET or something along these lines. SONET would be fiber optic. But within a building, for example, almost all cabling is Ethernet today. So Ethernet is the champion when it comes to our media type. Earlier media types that used baseband transmission technologies were token ring and ARCnet, Advanced Resource Computing Network, or Attached Resource Computing Network. So these two older technologies, token ring and ARCnet, also were baseband technologies where only one node is allowed to transmit at a time. Those last two, the token ring and the ArcNet, are considered to be token passing technology. We'll talk more about that later. Now, the competing technology to baseband is broadband. Broadband is the newer, rapidly growing technology where multiple data signals can occupy the same common media without destroying the other signals. In other words, multiple nodes can transmit simultaneously on one conductor, on one media type. And so this is called broadband. And as you can probably figure out, broadband, because it allows multiple data streams on a single wire, is much more efficient. It has a much higher data rate, and it's used in larger, faster networks. Now, the kicker, though, is typically broadband technologies are more expensive than the baseband technology. If only one guy is allowed to use the wire, of course, it's slower, and of course, the electronics are relatively cheap and easy. But if I need to squeeze 2 or 10 or 20 or 200 nodes on the same wire simultaneously, you can imagine the electronics that support that system are substantially more complex and therefore more expensive. So broadband has substantially higher data rates, more data throughput in the same period of time, but it is notably more expensive. How do we get those different data streams onto the media and not allow them to destroy somebody else's data stream that's concurrently on that same media? We use something called frequency division multiplexing. Typically, this is a radio frequency, which is electromagnetic waves, a radio frequency wave across a coaxial cable. And this allows for one signal to propagate at, let's say, 10 megahertz, and I can send a second signal, let's say 13 megahertz, and a third signal at 17 megahertz, and a fourth signal at 19.2 megahertz, and I use simply a different frequency for each transmitting station, and of course the destination must be tuned to that same frequency. So now what we're seeing is we have electronics that are not just turning on a voltage or turning off a voltage, but they are actually producing these electromagnetic waves, which are sine waves at a specific frequency, but the destination must be tuned to that same frequency, so we have to coordinate all that. And if you have to operate at different frequencies, you now have a very complex transmitter and receiver series to communicate across this same broadband media. Frequency division multiplexing uses different frequencies for the transmitter-receiver pair, but I can put those differing frequencies on the same coaxial cable. So one cable run, and I'll splice out on the destination side to 10 different nodes, but only the nodes that are tuned to my frequency can understand my signal. The good news is I can put 10 or 20 or 200 different signals on that same coaxial cable simultaneously and share that one cable with many data streams. A newer and also very high efficiency and very expensive broadband technology uses wavelength division multiplexing. Now, wavelength relative to the wavelength of light waves. So now we're using photons, not radio frequency electromagnetic energy. We are using optical energy or photons, light pulses across a fiber optic cable. And as we had discussed when we were looking at the different media types, fiber optics are one of your best media types when it comes to efficiency, the ability to carry multiple data streams using wavelength division multiplexing, the lack of emanations, the lack of interference, the greater distances, and the greater security. So this wavelength division multiplexing over fiber optics is the bomb these days. With very high data throughput. The problem, though, is it is notably more expensive, yet still it is notably more secure. All right, all that said, we've covered these two definitions thoroughly, and we will pick up shortly where we left off. In this lesson, we're going to look at Ethernet. Ethernet uses what we call twisted pair cable. It's a total of 8 wires in one jacket and one cable. We take those 8 wires in pairs, and each pair will consist of one wire that's going to carry the data signal, and this second wire is going to be grounded. And then we're going to twist these two wires together. As you can see in the photograph here, we have then 4 pairs of wires that are twisted together. And the grounded wire that's wrapped around the data carrying wire is twisted around that wire so that it will disrupt the electromagnetic field that is emanated as the electrons flow, the signal flows through the data carrying wire. Now this reduces the emanations. It's not terribly effective at reducing it, but it's better than nothing. And it helps to allow the data run, the cable length, to be greater, and we can still have enough signal at the end of the cable to understand what the signal is. So we use this twisted pair cable for our Ethernet networks. We notice that the connector at the endpoint has 8 pins, and it's called an RJ45 connector. So those pins actually are what plug into the back of your computer in the network interface card and plug into the wall jack, which is an Ethernet cable behind the wall, but it's the female portion of this RJ45 connector. And then, of course, those 8 wires connect to 8 pins that are part of this RJ45 connector. Now we have unshielded twisted pair, and that is the single most dominant cable type or media type for networks today. All of our data centers have miles and miles of UTP, unshielded twisted pair. And businesses have this UTP in the walls, in the ceilings, etc., that connect all the offices together, back to the wiring closets where the switches and routers live, and to the data center where all the servers live. So that is almost all Ethernet. Now, there's another form of twisted pair called shielded twisted pair. And on the slide, as you can see down below, the very bottom image is a photograph of shielded twisted pair. And what you'll notice is there are 4 pairs of wires, just like there was with unshielded twisted pair, but surrounding that series of 4 wires is a plastic mylar sheet, very super thin plastic sheet, but it has been coated with a very thin layer of conductive material. So we wrap this, it's almost like a foil. We wrap this foil around the 4 twisted pairs, and then we ground that foil at the endpoints. So this produces an extra layer of shielding around the data carrying wires. So this is our shielded twisted pair. Now, shielded twisted pair has better emanations protection, less signal propagates out into the air around the wires, and it has better protective shielding so that emanated signals outside don't induce so much signal into our wires. And it allows for slightly longer cable runs because of the greater efficiency keeping the energy contained within the wires. However, the cost and the difficulty of using STP is so high, the benefits aren't worth it. So if you have emanations or efficiency concerns, STP typically is not your solution because it's notably more expensive and the benefits are only marginally increased. So UTP is by far the dominant technology. As we twist the ground wire around the data carrying wire more and more and more, eventually if you twisted it very, very much, you would have a ground wire that was completely encasing the data signal wire. However, the problem is that consumes a whole lot of material. You just took a 100-meter cable, and because you twisted it up so tightly, it's now worth 15 feet of distance. You really can consume a tremendous amount of material by increasing these number of twists. Well, studies have shown us how many twists per foot it takes to get a certain level of improved performance out of the twisted pair cables. For standard voice, which is like your telephone cabling, it's called Category 1 cable, and it has approximately 1 twist per foot. In other words, the ground wire wraps around the data wire. The data wire is now carrying your voice data, analog type data, once per foot. And so Cat 1, Category 1, has approximately 1 twist per foot and is generally only used for voice. You notice there's no digital signaling, no data on that other than analog voice data. Category 2 has approximately 2 twists per foot, and it generally is good to conduct about 4 megabits of signal, data signal, over about a 100-meter span. Cat 3 is 3 twists per foot. It gives us about 10 megabits per second. Cat 4, approximately 4 twists per foot, 16 megabits. Category 5, which is where many of our networks were installed, gave us 100 megabits. Today, we want greater data rates, so we're looking at gigabit Ethernet. And now we can either use a very highly refined Category 5 called Cat 5e to get 1 gigabit, but Category 6 was intended as the 1 gigabit per second UTP type of cabling. Now, we have 10 megabits baseband using twisted pair, that's 10 base T. 100 megabits baseband. Remember, baseband says 1 signal per conductor only and ever. If a second signal hits the conductor, we've destroyed the signal. And again, so 100 base T is 100 megabits baseband twisted pair. 1000 base T is 1 gigabit per second baseband twisted pair. There are also cables called crossover cables in Ethernet where these pairs of wires, one pair is typically considered a transmit pair and one pair is considered a receive pair. The cables are built so that the transmitter and receiver pairs are plugged into a hub or a switch, and that's where they connect to the destinations. Transmit connects to the destinations receive. So the crossover occurs in either the hub or the switch, some central connecting device, and we'll be talking more about these devices later on. So the crossover occurs in this intermediary device, a hub or a switch. However, if I needed to connect 2 computers directly together, I would buy a crossover cable that connects the TX directly to the RX on the other side of the wire, on the other RJ45 on the same wire. In this case, my TX pair on one endpoint connects to the RX pair on the other connector, and vice versa. My RX connects to the other end's TX. So the crossover occurs in the cable because there is no intermediary device like a hub or a switch. Now, there was another area of concern relative to the jacketing on these cables. Historically, PVC, that's polyvinyl chloride jacketing, is used. And by the way, that's what almost all of our cables are today. However, the problem is it burns at a relatively low temperature, and when it burns, it emits poisonous fumes that will kill people. For fire safety, if there are concerns about the jacketing of the cable, that if it burns, it's going to injure people, there is a jacketing that uses a different chemical that burns at a much higher temperature, and therefore the toxic fumes are not quite so prevalent with a standard fire. And this is called plenum-rated cable. And it really, plenum-rated simply says we use a different chemical for the jacketing, but that chemical burns at a much higher temperature. In other words, it doesn't emit those toxic fumes when it burns so readily. And typically this is what is used inside the walls or in the crawl space if there is a high risk of fire. So this plenum-rated cable is notably more expensive, therefore not commonly used, and in most cases we've come up with solutions where we don't need to buy the plenum-rated cable versus our standard Ethernet cabling. In this lesson, we're going to be looking at the wireless media transmission technology. Just an introduction, we've got a whole section on wireless later. So in wireless networking, the Institute of Electrical and Electronics Engineers defined a specification for wireless local area networks, wireless LAN as they call it. And that specification is defined as 802.11. So the 802 series deals with communications over networks, and the 11 series, 802.11, says wireless networks, wireless local area networks. So that's where this specification comes from. Now, they define the electronics and the radio frequency transmissions, the frequencies that have been allocated by the FCC are utilized and built into these specifications. Signaling schemes, the way we modulate and encode the data into the radio frequency energy that is propagated out into the airwaves as the wireless signal. This is all defined by the 802.11 specifications. Now what happens then is the manufacturers of wireless access points and wireless network interface cards, they have to interpret those specifications and then implement them in their electronics and the software that controls those electronics. They have to build these radio transmitters and receivers using specific types of antenna that meet the specifications. Frequency controls have to be in place. And so the vendors of the wireless components have to meet these 802.11 specifications as defined by IEEE. And of course, the FCC allocates specific frequency ranges for these wireless networks. Now, the great thing about wireless networks is they are easy to install and they're inexpensive. Why? Because you don't have to buy any cables. You simply buy an access point. Now, you do plug the access point into the Ethernet network, but then the signal is propagated from the access point out to the wireless clients using the airspace. And as a result, there's no need for cabling. So it makes it very efficient. Your users can relocate from one cubicle to a different cubicle. They can go from their office to the conference room, to the break room, whatever they want, and they can still stay connected. This is called roaming in the wireless network. It's a very fast and efficient way to get nodes connected to the core network that is wired. This would be where your servers are, where the resources live, the file servers, the other resource servers, perhaps connectivity to the internet. So we'll connect wirelessly between the laptop, as we see in the slide, back to the access point. And then we use a wired network from the access point back into the core network to get the resources and perhaps even internet connectivity. This is how the wireless network operates. Because the wireless emanates its data signaling into the air, it is least secure. In other words, a bad guy simply has to fire up his laptop and he can eavesdrop on every transmission that occurs between the access point and the client nodes. And it also is most susceptible to interference from other radio frequency sources. So we have these problems that we have to deal with. This is one of the reasons why there are power limitations in those 802.11 specifications that say your access point can only propagate at this power level, trying to contain physically the space that you are emanating your signal into so that you don't somehow interfere too heavily with the wireless networks adjacent to yours, on the floor above and on the floor below and on the offices through the wall. These power specifications in 802.11 specifications help to control that and keep the size of the propagated cell, as it's called, to what we would consider to be a functional local area network, and hopefully not much past that. Again, the primary hardware associated with the wireless network is the access point that typically gets a Ethernet cable attached to it back into the core network, but then it is the connection point for all the wireless clients within its cell. So the cell is the area of radio frequency propagation, physical space, and all the nodes that are associated to this access point. So that's the definition of the cell. We'll be looking at wireless networking a lot more in a later section in this series of lectures.